Now, whenever starting one of these new problems, as you know, I always recommend that you draw a picture, and that's going to help you get your head around what's going on in this situation. So go ahead and draw a picture of this if you haven't already. Now, if you're particularly artistic, your picture might come out looking something like this. But really, we want to focus on the geometry that's going on behind all this. So what I see as I take a look at this is I see one really big triangle out here around the outside. And that specifically is a right triangle. Okay, then what's going on with Homer and his shadow? Well, you notice that that is another right triangle. And so really we have these two right triangles that are overlapping each other here. So this whole problem can boil down to basically just being some geometry here, where we know we're taking a look at a couple right triangles, and now we need to start figuring out, okay, what's really changing? What do I have to label? And actually start doing some labeling along the way here. And this problem poses a potential problem and a potential conundrum for us, because as we take a look at it, what do we want to label? So like when dealing with the little triangle, okay, we might see that one a little bit easier. We might go ahead and call this S for being the shadow length, and then we would have Homer's height. And then this length right here, notice that that's just the path that the beam of light is traveling right over his head. That can be a little bit tricky. I'm just going to use L for length there, but notice that's not the shadow length. Shadows are along the ground. Sometimes I'll see people try to label this as the shadow length and it throws them off. So just make sure you're keeping that part straight. But if we labeled that one like that, then I'd have to go to the bigger triangle. And in that bigger triangle, what would I label this? Would I label like that whole thing as D? Or would I want to maybe just label this length here as D, the distance? And each of those strategies has some potential pros and cons to them, but it really is going to make it tricky depending on how we do it. So what I would recommend is that for our big triangle, we actually just label each of these individual lengths. So I'm going to label D as being this length here, not the entire length from the lamp to the end of his shadow, but rather the distance from the lamp to Homer. And then we have the height of our lamp. Well, I don't really want to use H for that as well, do I? Because I already have H over here. We got the height of Homer and we got the height of the lamp. Okay, well then maybe you're thinking, okay, lamp, it's L. But we already use L for the length over here as well. This is where this starts getting a little bit tricky, as you're seeing. There's some ways around it, like you could call it like H0 for the height of the lamp and H1 for the height of Homer. That's a good way to get around it. That's often used in math and science as a way to be able to deal with multiple values with the same name. I'm going to run with it for the moment. If I follow that same kind of a format then I know that I could use L1, oops, nope, I'm going to use L0 for the length of the beam of light heading from the lamp to the top of Homer's head, and then I'd call it L1 from Homer to the end of his shadow. And you might be right now thinking, whoa, this is a lot of stuff, but the good news is you actually don't even need all of these, as you'll see. We're only going to need a couple of them, because there are basically two big ways that you could go about doing this. The first would be to set up Pythagorean theorem for both triangles. But you notice that if we do that, we now have two equations with all these variables in them. And my next step would then be that I have to figure out some way to combine them into a single equation, which yes, can be done, but it's going to be somewhat tricky because we're going to have to like go and figure out, okay, what does L1 equal? And we'd have to like get the square root of both sides. And then I have to take whatever that value of L1 is and plug it in for L1 in the other equation. And then I could worry about taking like the derivative with respect to time at that point. Yeah, that's going to be way harder than this one really has to be. So instead, I'm going to focus on what's actually changing in this situation. And so since the H's aren't changing at all, I'm going to go ahead and ignore those, at least for the moment. And then the L's and the D and the S. Okay, both of those are changing as he's moving outward, but we only really care about one of them. All we really care about is the shadow's length. And since we care about the shadow's length, that means really we need to just be dealing with these, because we could figure out how quickly those are changing, but we just don't have to. So I'm just going to focus on those two. Now, to be very specific then, that means that D is my distance from the street light out to Homer. Then S is the length of Homer's shadow. So notice that I'm taking this division right here between them. Don't get that confused, or this problem is going to be very difficult from there. Now, I can get away just by using D and S as variables because of some geometry I know about this situation. Now, we're talking about a situation where we have two right triangles, and you notice that we know those angles are the same, and of course the shared angle must also be the same. Notice, that is enough to prove by angle that these two triangles are similar. Yes, there is actually a use for some of those proofs back there, and the similarity and congruence and all that kind of stuff from geometry. These are similar triangles, which means that I can set up some proportions to figure out their side lengths. So I'm going to go ahead and finish labeling out my diagram here with the numbers that I know now. So I know that the height of Homer is 6 feet, and I know that the height of the street lamp is 18 feet. Then I just want to put on here the fact that he's running away at 8 feet per second, just so I can keep track of that. And we know that this 100 needs to be in there someplace too. Now think about, where would that 100 actually go? So that 100 is the distance from Homer to the light. So that means that our D value is 100 feet. And again, that value again is just between these two ends here. So it's just the distance between the light and Homer there. Now I'm going to set up a comparison of side lengths in these similar triangles. So for instance, I could do little triangle over big triangle for their heights, 6 over 18. And then I could set up the same kind of ratio for the base down here. Now I'm going to leave it in terms of D and S. I'm not going to put the 100 in right now because remember, D is changing and therefore its derivative will not be 0. And if I just plugged in the 100 now, we'd be pretending that it would be 0. So I need the length of the corresponding side in the small triangle, that is S. So that's on the top, because remember, it goes small triangle over big triangle in the first fraction. Therefore, I have to do small triangle over big triangle in the bottom, in the second fraction as well. And so in the top, it's S. In the bottom, then, it has to be the entire length here. So notice that's not D. That's D plus S. This is the hardest part about this problem right here, is just getting that proportion set up. Once you've done that, the rest of it's going to be fairly straightforward. It's just a matter of doing the math. But seeing how we get that proportion set up in the first place, that's the tricky bit. So make sure that you've seen how to do it. Rewind, see that explanation again if you need to, and we'll do more practice with it as well, but that's the critical piece that you really need to make sure you wrap your head around. All right, so let's go ahead and move on from here and actually figure out our answer. Now, I could actually find the derivative with respect to t right now, but that would mean having to use quotient rule, and I don't really want to deal with that. So I'm going to make my life a little bit easier. I'm going to start by cross-multiplying this proportion. If I do that, then I have 6d plus 6s equals 18s. And I could go ahead and find the derivative here, yes, but I'm again see a way that I can make my life a little bit simpler in the long run. So I'm going to do that just because if there's a way I can make it easier, I want to do that. Because I see that I can move the 6s over to the other side, and that's going to combine both the s terms. So I'm going to subtract 6s from both sides. So that will turn that into a 12s instead. All right, I'm going to go ahead and work with it from here. Some of you might be seeing, wait, can't we also then go ahead and divide both sides by 6? Yes, we can. And by all means, feel free to do so. But I'm going to leave it here, mostly so that there's fewer moving parts and therefore fewer things that might throw somebody off when we're first learning how to do this particular process. All right, so now that I am here, I am going to go ahead and find my derivative with respect to t. That's just going to be 6 dd over dt equals 12 ds over dt. Well, we know one of those values. Remember that we know that Homer is running away at 8 feet per second. Now, think again here for a moment before we plug it in. Which value is that actually changing? Is that changing how the D is changing, or is that changing the S directly? Which one of those would be 8? The answer is that it would actually be the D value. The S is unaffected by that because S is changing, but as Homer gets further out, the shadow length is going to be changing at a different rate because the angle is changing. And so it's going to be that D value. The other thing that we could know is that we're being asked here in the first place, how fast will the length of the shadow be changing? Well, that's ds over dt based on our drawing. And so, of course, we wouldn't know what ds over dt is at this point. So let's go ahead and plug in for dd over dt. So that would turn that into 6 times the 8 equals 12 ds over dt. And then go ahead and solve that out for ds over dt. And we should find that the length of the shadow at that moment is increasing by 4 feet per second. All right, so that means that the shadow's length, specifically just the shadow, is increasing by 4 feet per second. Now, some people get a little mixed up at this point. They think, wait, shouldn't it be like more than the 8? Well, it depends on what the angles are involved. It would need to be more than 8 if it were the rate at which that entire length was changing. But because we're just looking at this portion of it, just that shadow length, it's not necessarily going to have to be more than the 8, although it can be.